Hey guys, hello everyone, and very welcome to the SYN Academy, all of you. This is Jagriti Sharma, and you are going to watch the E2 elimination reaction. And guys, E2 elimination reaction का जो application है, that is what we are going to see in this particular video. Now, a common question that students ask is, ma'am, we have already done the reaction mechanism. We have understood everything about the reaction mechanism, all the different types of reaction we have done, but still we are not able to attempt questions in the CSIR net or gate examination. Why is that so? Now the answer, one of the important points is that when we have understood the reaction mechanism, we have studied only the reaction mechanism part, that how a molecule is reacting, okay, but there are a lot of aspects in in the examination which is put together along with the reaction mechanism. और सबसे बड़ा factor है stereochemistry, okay. So as you can see, I have taken in this particular slide, I have taken E2 elimination from cyclohexane. This is very confusing to a lot of students. Let's get started guys, and let's understand that how a particular cyclohexane molecule just like this one is going to react in the presence of a base. Okay, so you see over here I have two different diastereomers. This is one diastereomer, this is another diastereomer that I have. Alright, so these two different diastereomers are going to give you two different products. Elimination of diastereomer A gives you two products with a ratio of 1:3, and elimination of the diastereomer B gives you this one product, but it is 250 times slower than the first one. Why is that so? Why is this happening? Now if you have seen this exact example has also been given in the Carruthers book. If you have studied, you will know it has also been asked in your CSIR net examination directly. Okay, so first thing we are going to see is, in the E2 elimination reaction, what is the condition that we want? We want 180-degree condition. We want anti-periplanar nature, anti-periplanarity of this Cl, and a hydrogen on the adjacent carbon, either this one or this one. So we are going to see. First thing, in the first diastereomer, you have a hydrogen in both the on both the sides, both the vicinal carbons. So look over here. This is the Cl, and there are two hydrogens present. Now, when you have to draw the conformation, you will try your best and draw the more stable one. So this is the more stable conformation of this particular compound. Just stop the video and see it properly. That the isopropyl group is below and it should be equatorial. Cl is below along with it, and the methyl is trans, it is opposite, so it is opposite put over here. Now the isopropyl will favor equatorial position, so that's why this makes the more stable isomer. And do you have a hydrogen anti-periplanar to the Cl? Absolutely you do. In the more stable, this is the more stable isomer over here, and here itself you have two hydrogens which are anti-periplanar to the Cl, so elimination is possible. Now the question is, which one is going to eliminate? Which hydrogen will eliminate? That gives you regioisomeric products. That is, look over here, the two alkenes which are formed. This is a Hofmann alkene because it is only di-substituted, and this is a Sadzeff alkene, it is tri-substituted. So these two are regioisomers of each other, only the double bond position has changed, right? So which one is going to leave? If you are having a base like ethoxy, which is not a very bulky base, I just hope that you have seen the previous video regarding the elimination reaction. We have discussed that halides like chloride, bromide and iodide, they will tend to give you more Sadzeff product as compared to Hofmann. Okay, so here it is your chloride and it's going to leave, and this is driving the hydrogen. If the base is not too bulky or if the substrate is not too bulky, then definitely it is going to give you a major of the Sadzeff alkene, which has exactly happened over here. This is your Sadzeff product, tri-substituted alkene. and this is Hoffman, which is formed in a lesser ratio, let's say 25% of this and 75% of this. All right. Now, there's no need to go to the disfavored, conformation in the first example. Okay, fine, we move onward to the next because यहाँ पे हमारा favored वाले से काम हो गया, ठीक है. Now we move onwards to the next diastereomer. Look at diastereomer B. Now over here, what do you see is you have, again, you will try to draw the more stable conformation. More stable conformation may isopropyl will be on the equatorial position. Chlorine is opposite, so it goes above equatorial. Methyl is above equatorial. Now, this is the more favored conformation, but unfortunately, you don't have the Cl on the axial position. You always want the leaving group on the axial position in the cyclohexane, otherwise, no elimination will happen. So, we have to do the ring inversion, करना ही पड़ेगा ring inversion यहाँ पे, and then you see that this isopropyl group, it goes below the plane and it goes axial. That's why it is less favored, because it is having the 1,3 diaxial interaction over here. Okay, but fine, chlorine is still above and axial, so we got the chlorine axial. We got only one hydrogen. This is only one hydrogen which is anti-periplanar to the Cl. The other hydrogen goes equatorial. So only one possibility of the alkene formation, no other isomer possible. Now you must have understood why it is giving you only one product, diastereomer B, and why it is 250 times slower than the first reaction, because here you have chosen the less stable conformer, hence a slower reaction as well. This was put up as a direct question in the CSIR net examination. Whatever you have understood about the E2 elimination reaction on cyclohexanes, please try and do this question. Try to apply the same knowledge over this question. Okay, so read out the question, stop the video, do it by yourself, and then you can see the solution. All right, so yeah, let's see. Basically, the question is asking you, you are having one and two different types of bromides. One of them is going to give you alkene A, that is this one particularly, and none of them give you alkene B. Now, alkene B की शक्ल देख के पता चल रहा है, why does nobody give you alkene B? Because here this carbon is a bridging carbon, so it's going to be difficult to form a double bond or a carbocation on the bridging carbon. That is not allowed by the Brett's rule, right? So first of all, we will try to draw the conformation of this particular cyclohexane, let's say. Now this is one cyclohexane, and you see both of the groups, that is, it's a carboxylate group, so it is attached above. So I will be writing it in this way, for example, roughly writing it in this way. Now you see that there is a bromide which is below and it is on the side of oxygen, so I will write the bromide over here, it is below. Now in this particular conformation, the conformation is locked. Why is it locked? Because the cyclohexane cannot flip and there's a carboxylate group which is locking it. But in the locked conformation, it is happy, it is having an anti-periplanar hydrogen. So in the presence of a base, it can remove this proton and it can undergo anti-elimination like this to give you an alkene in this way. How is the alkene going to be? Exactly, which is given in the option, which is given over here, alkene A, right? So it is possible. Now the next compound, or the compound number 2, why is it not able to do elimination? Let's see for it. So this is your molecule once again, or let's say drawing it the same way. You are having a bromine above this time. This bromine is above the plane. If it is above the plane, you cannot flip it, you cannot take it in the axial position, it is equatorial over here. So equatorial bromide cannot undergo anti-elimination because there is no anti-hydrogen present to it. So bond does not break like that. So the second one is not going to undergo elimination, as well as alkene B cannot form. Now let's try to form the structure of alkene B. if we try and write it like this, you have the double bond on the exact carbon where there is oxygen connected, and this is a bicyclic compound. Now you cannot have a double bond on the bridging position, forbidden by the Bread's rule. So this is the answer to why not. Just try to do more and more examples like this. You will get them in the book, in the previous year questions. All right. Similarly, you must try out one more question which is very, very important, very easy to do. So the question is, account for the contrasting result of these two reactions. What are the two reactions? As you can see, in one of the molecule, you are having a tertiary butyl group to attached to the cyclohexane, then a bromide, and then a carboxylic acid group. Right. So here the only difference is you are having a carboxylic acid group above, and this one over here is written below. It is going to be below over here. All right. Now, these two compounds, these two diastereomers, in the presence of a base, are giving you two different compounds. Why is that so? Try to write the mechanism by yourself, okay? And then we do the reaction by reaction mechanism over here. Okay, so it would be very, very simple if you just try and write the cyclohexane conformation for both of these, okay? So we want to do E2 elimination. So there is a hydrogen anti-periplanar to the bromine in the first compound. In the first compound, there is a hydrogen which is anti-periplanar to this bromine. So E2 elimination is possible in the presence of a base. Base takes away this proton. There is going to be a double bond which is formed, and the bromine is going to leave. Ultimately, what do you get is, I cannot write the cyclohexene in this way. It is not correct to do so, but just for understanding, okay, you get this molecule, and after that you can just write it like this, because abhi double bond ban gaya hai, so it is planar, right? In the second compound, you see that there is a base and the carboxylic acid group is below, so we are doing decarboxylation along with elimination of bromide. So it is not just E2 elimination reaction anymore, it is also decarboxylation. Why does that happen? That happens only because the COOH group was present anti-periplanar to the given bromide, and the hydrogen is not anti-periplanar, right? So it's a very, very important reaction. Again, it has been asked in the CSIR previous year questions. You can open up and see. So direct question from the solution manual, along with the elimination of Br minus, you also have COH eliminated, decarboxylation and elimination. Very, very beautiful. Right, guys. So we have another very important type of elimination reaction. It is not only the E1 and E2 elimination that we have to study, we also have to study pyrolytic SYN elimination reactions, right? So if you have noticed, the E2 elimination reaction, all the times we have been talking about anti-periplanarity. We want the hydrogen as well as the leaving group to be anti-periplanar to each other, right? But here we are talking about the leaving group and the hydrogen being on the exact same side. Right, guys, so we have another very important type of elimination reaction. It is not only the E1 and E2 elimination that we have to study, we also have to study pyrolytic SYN elimination reactions, right? So if you have noticed, the E2 elimination reaction, all the times we have been talking about anti-periplanarity. We want the hydrogen as well as the leaving group to be anti-periplanar to each other, right? But here we are talking about the leaving group and the hydrogen being on the exact same side, that is on the SYN position. How is it possible? Let's see. First example that we have of SYN elimination is xanthate elimination. All right, and what do you mean by pyrolytic? That is in the presence of heat. So we are not providing any reagent to this system. We only have heat, and the xanthate elimination is taking place. Second example is selenoxide elimination. We also have many more examples, that is acetate pyrolysis, cope elimination. We will see all of them eventually. All right. So first example that we see over here is xanthate elimination. I know that you remember, as soon as I say xanthate, you must be able to remember the name reaction which is associated to it, and that is Chugave elimination reaction. Okay, guys? Yeah. So let's say you are having some alcohol. Let's say this is some alcohol like this. So alcohol के ऊपर हमने लिया sodium hydride. You have seen this many times in the previous year question. You are taking a sodium hydride which is going to deprotonate the alcohol. You are going to get O minus. अब ले लिया हमने. We have taken carbon disulfide in this way. So carbon disulfide along with methyl iodide. What is that going to do? The O minus which was formed is going to attack on this carbon. The pi bond is going to open up and attack on the methyl, and the I minus eliminates. You are having the xanthate repaired. अच्छा एक सेकेंड, ये ऑक्सीजन नहीं आएगा. Just 1 second. Now you will have the oxygen connected to C double bond S and one SME. ठीक है? This is the xanthate salt. It is looking for a hydrogen which is on the same carbon over here. But in this example, I have not given you a same side hydrogen. I have put all of these as R groups over here. But anyways, it is looking for a hydrogen on the same side. If there was a hydrogen on the same side, it can just do elimination like this, which is the xanthate pyrolysis. All right. So it is very, very easy. Now, this is your xanthate. Always use the double bond S to remove, right? To remove this proton over here. So this double bond attacks over the proton. The carbon hydrogen bond breaks and falls over here. Carbon oxygen bond breaks and falls over here. Eventually, what you are getting is this particular compound, right? And alkene. Now, sometimes this particular compound, which is the byproduct, also breaks down. You have a hydrogen over here on the sulfur. What happens is the SR bond is going to, this bond is going to attack over the proton. This bond falls over here. You are having C double bond O double bond S as the leaving group. Or ye, it is just like carbon dioxide linear, and it's volatile in nature, and then you have thiol. Okay, it can further break down as well, right? Now this is exactly the same. It is the Chugave elimination reaction, which is very, very popular. It is a pyrolytic SYN elimination reaction. Second important reaction is selenoxide elimination. Now you will see the mechanism and you will notice one very important difference. What is that? Here we have taken selenium oxide. How do you get selenium oxide? कैसे बनता है selenium oxide? Very, very simple. Let's say we are having this molecule where you only have the selene like this. Now when you are treating this with metachloroperbenzoic acid or any other molecule or any other reagent which has electrophilic oxygen, which is able to deliver an electrophilic oxygen to a nucleus which has electron density like this, which has a lone pair basically. So you do this oxidation, heteroatom oxidation over here, right? So this heteroatom oxidation is going to give you selenium oxide. In the presence of heat, the O minus takes away this proton, the bond falls over the carbon-carbon bond, and this bond falls over selenium. Now you see it is only going through a 5-membered intermediate, and Chugave elimination or xanthate pyrolysis went through a 6-membered intermediate. The product is the same because here you don't have a lot of difference in the substrate structure. So you are getting the same product and you are getting the selenol compound. Finally, it's like the alcohol. The difference will be very clearly visible when there is a possibility of getting the Hoffman and the Sadzef alkene. Most of the SYN elimination या SYN pyrolytic elimination reaction prefer to give Hoffman alkene, that is the less substituted alkene. But even if you are getting some amount of Sadzef alkene, that will only be given by the six-membered transition state or by the Chugave elimination or acetate pyrolysis. ठीक है, acetate pyrolysis is similar because it goes through a six-membered transition state. The five-membered transition states one, these the selenoxide elimination, cope elimination, they will always give you Hofmann alkene without any doubt. If you have an unsymmetrical alkene, it is always Hofmann by the five-membered. So we move onwards and see more examples. All right, guys, look at these beautiful examples. Now, these examples are taken once again from Caruthers, and you can see one by one what is taking place, what reaction is taking place over here. So you see that the first one, it is not anymore the xanthate pyrolysis that we were doing. What is it now? Now it is an acetate, as you can see. It is a carboxylate group, COO, and the whole thing. So we will call it the acetate pyrolysis. How do you form the acetate? It is very simple. Just like you provided CS2 carbon disulfide, just like that you can provide CO2 and methyl, or through a different mechanism also. Acetate formation is very simple. So always acetate pyrolysis goes through a six-membered transition state, as you can see. All right, it again goes through a six-membered transition state and it gives you this product. All right, here we have only one possibility. Why does the deuterium eliminate? Why does the hydrogen not eliminate? You might have also got this question, that why the hydrogen is not being picked up. Because if you rotate this hydrogen and put it over here in the position of deuterium, both the phenyls would be on the same side. Look over here. Both the phenyls will go below the plane. There is a hydrogen over here, there is a deuterium over here. This hydrogen is being picked up from the acetate like this, in this way. So you see the interaction is going to be bulky, less preferred, and that is why the removal of hydrogen is not preferred. It is the deuterium which is removed. So you have also got to consider the steric interaction. That's why this is the product. In your examination where you are having MCQs, you will be able to answer based on the options. If your basics are clear, option देख के समझ में आ जाएगा कि which product is the major product. Okay? All right. Now, moving onwards again, yes, is it the same compound that we have got over here? No, it is the isomer. Why? Because the position of the pH, pH, everything is the same, but here only the position of deuterium and hydrogen has changed. So this is a diastereomer of the above compound. All right. So again, in this particular diastereomer, you will be able to remove the hydrogen because both of the phenyls are still trans to each other. So steric hindrance is still low over here. So diastereomer 13 gives you 61% of the product yield, but this diastereomer gives you 74% of the product yield because hydrogen removal is faster, more preferred, which is also there in the good, stereochemically it's also good. Not much interaction. Now, third example, as you can see, very, very simple, guys. What are we doing? You are having the acetate group over here and here in the bottom also, in the top also. You are looking for a syn hydrogen. You have one syn hydrogen on this side, another on this side. You just need to see this is your acetate, this is the syn hydrogen. Do the elimination, you get a double bond over here as well as here. How easy it is. So once you understand the concept, it is very easy to answer. Okay. All right, another very beautiful example. Now this time we have taken cyclohexane examples to consider that what is going to be the major product of the acetate pyrolysis reaction once again. So you see the example number 18 over here. Again, this has been taken from Caruthers. Okay. Now see, it's not confusing. If you look at this structure, it is very easy to understand that which is the acetate group which is going to leave. Okay, whenever you have an oxygen directly connected to this carbon, this is going to be the leaving group. rather than this carbon, this ester group, right? Both of these are ester, but here this is the leaving group. Now the question is, who is it going to take away? Where is it going to take away a proton from? It's looking for a syn hydrogen or a same side hydrogen. There is heat, so it is pyrolysis. Which hydrogen? It is below the plane. The ester is also below the plane, so it has only one possibility to take away this hydrogen along with it. So I'm writing O, C double bond O in this way. This carbon also has a methyl. Okay, I've just opened it up and I'm writing the mechanism in this way. What happens next? You have got this alkene over here, and along with that you are going to have the ester, MEC double bond O and OH. Yeah, you have an acid. This is a cis diastereomer, this is a trans diastereomer. That's the only difference. Now again you have the same leaving group, that is going to be your acetate, but it is above, so it's going to look for this hydrogen which is also above, as well as you have one more choice. This hydrogen is also above. What did I tell you? I told you what is going to be the major product. Now when you have a possibility, in the first case you did not have a possibility, you had only one hydrogen which is on the same side, that's why this is the only one product possible. In the second one you have a possibility. When you have a possibility, if the reaction goes through a 6-membered transition state, you are always going to form the more substituted alkene. Okay, so if you remove this proton from here, that gives you the same alkene, you will get the same Hofmann alkene. If you remove a proton from here, you get this one, and this is the major product. Why? Because the 6-membered transition state leads to more stable or the SADESF alkene. Alright, how beautiful this is. Let's move onwards and see more examples. Now you see, this reaction, cope elimination, is just like selen oxide elimination. So we are getting the amine oxide by doing the oxidation on this particular amine. So you have two different diastereomers once again. Here the isopropyl group and the amine, they are trans to each other, and in the second one you are having the amine oxide below the plane. So try to just stop the video, draw the conformations and do the mechanism by yourself for better understanding. यहाँ तो हम देख ही लेंगे कि देखो, when the amine oxide is above the plane, it is trying to pick away a hydrogen from above. Who are above? ये भी बीटा कार्बन पे है और ये भी बीटा कार्बन पे है, and they are on the same side. So we are looking for syn hydrogens. Absolutely. Okay. Now, as I had told you, amine oxide goes through 5-member transition state. तो 5-member transition state है इसका, और यहाँ choice है. There is a choice, but it is going to select this hydrogen, and it gives you a major of the Hofmann alkene. So when there is choice, the 5-membered one is going to give you a major Hofmann, and the 6-membered one is going to give you major SADESF. Alright, I just hope that I have emphasized enough on this point. Please remember, given that there is a choice. अब देखो second वाला जो है, here the amine oxide is below, or below में there is only one possibility. This side there is the isopropyl below, and this side only one hydrogen is below. So here you don't have a choice, only one possibility. That's why इसी को निकालेगा and you get only one product. Okay, no major minor possibility. So this is it, guys. We have discussed some really important reaction. SYN pyrolytic elimination is equally important as compared to E2 or E1 reactions, and it is kind of an advanced advanced kind of mechanism. And all of these examples that I've taken to give elimination, acetate pyrolysis, selenium oxide elimination, amine oxide elimination, and just like selenium oxide, you can also do the same reaction with sulfur, because sulfur and selenium are there in the same group, so it will give you same kind of a reaction. Okay, so yeah, we are done. Yeah, it's going to be like this. So we are done for today. I hope that you are liking this video. If you are, please comment and tell me, and please also share it with your friends. and more videos are going to come up. I'll see you soon in another one. Take care, all of you. Have a nice day. Bye, everyone.